Okay, types of radioactive decay. So I'm just going to run through each type here. We have, that we're going to discuss, we have alpha emission. And this is where an alpha particle is emitted from a nucleus. And what this does, this is when you have a very large nucleus that's unstable. It can eject an entire nucleus, 2 protons, 2 neutrons. So it's just saying there's way too much clutter here. We got too much in this nucleus. Eject a full nucleus that contains 2 protons and 2 neutrons. So that's a really energetic thing to do. Then we have beta emission. This is the emission of an electron. Well, there's no electrons inside of the nucleus, so what happens is a neutron, if we look at just the individual process, a neutron breaks up into a proton and a high energy electron that takes off. So this is going to happen when, the thing that's wrong is that there's just too many neutrons. We're in the neutron-rich area of that band of stability chart. So in this case, we're not trying to just take a huge chunk of the nucleus away. Let's just change a neutron to a proton. Then everybody's happy. So this is what's happening to the individual neutron, but here's the case where we have carbon-14 breaks up into carbon-14 or nitrogen-14 and 1 beta particle. So here we have 6 protons and 8 neutrons. Now we have 7 and 7. So we reduce the number of neutrons. Now the positron emission is where we have a proton and we want to make it into a neutron. So we have too many protons. We're proton rich, and we can get rid of a positron and in the process create a neutron. So that's the individual process, but if we look at the full process of technetium-95, it changes into molybdenum-95 and plus a positron that takes off. And just add them up, see that we have, make sure that the equation is balanced. But then you see that we have 43 protons and then 52 neutrons. Then we have 42 protons and then 53 neutrons. So we've shifted things around, and in this particular case that makes the nucleus more stable. Then we have electron capture. This is probably, for me, it's the most interesting one, because a proton in the nucleus actually reaches out into the core electrons of the atom that it's part of and grabs an electron. And actually the electron electrons will travel through the nucleus, and while they're doing that, they will be captured by the proton. So they're not supposed to travel through the nucleus. We've always been told that they don't do that. They stay on the outside, but they do. And when there is that opportunity for a proton-rich nucleus to grab an electron and change itself into a neutron, it'll do it. So here we have potassium-40 grabs up a core electron, and this one will always be drawn like this. Previously, we had this beta emission. I drew it as an electron here, but I could have drawn this as a beta particle. And same thing here, I made this a beta particle, and that would probably be a better thing to do, because this thing, when it comes out of the nucleus, it comes out screaming. It's going really, really fast, so it's a beta particle. But this wouldn't be drawn as a beta particle because it's just a core electron. So you can see that when we add the electron in here, we had 19 protons, now we have 18 protons. So it did its job. Gamma emission is where we don't change the element. We don't change any of the either the atomic number or the mass number. What happens, this is called a metastable state. Electrons can be boosted up into higher energy states, we know that, but so can nuclei. So nuclei, where we have the protons and neutrons, they're in shells inside the nucleus that are analogous to the shells for electrons on the outside. And the protons or neutrons can be boosted up into higher energy levels. And when they're up there, they want to get back down into the ground state. And so when they do go into the ground state, they eject photons, or gamma photons. When electrons go from a higher energy state to a lower one, they eject electrons that are usually in the UV, visible, or the infrared range. But we're talking about nuclei here, so they eject gamma rays, very high energy particles. So spontaneous fission, and actually I messed up. You can see I made this into a 39. I had it as a 36, but when I added this up just before I did the lecture, I didn't come up with 92. So now it should be 92. 39 plus 53 plus 4 times 0, and then up at the top, hopefully, make sure, yeah. So this is when you have a very extremely large nucleus that where ejecting an alpha particle just won't do. In this case, it just simply falls apart into two nuclei that are approximately the same size, you know, are on the same size rather than tiny little particles. It breaks up into, so you have a huge nucleus that breaks up into two smaller ones. And then also they have an injection of neutrons in this case. So this is where it simply falls apart. So there's no, I can't give you this and ask you to tell me what happens, because even looking at this and then covering it up, I can't tell you. It's people who study this on a daily basis could tell you. But what I can do is show you this and ask you to tell me what type of process it is. Or I can hide away one of these and ask you to fill in the blank. But I can't give you a nucleus and ask you to tell me how it's going to spontaneously fall apart. But these other ones, definitely I can give you examples of, I can give you this species and ask you to tell me what the product is by gamma emission. Same thing here, I can give you just this species and ask you to tell me, write the equation for electron capture. So the other ones, definitely you can do that. You can, as long as you know what the process is, you can easily complete the reaction. Okay, then we have, starting with uranium-238, so the product after 6 alpha decays and 3, oh okay, so oh, I think this is supposed to be show the product. So in a we have 4 of these radioactive decay series, and the one that they show in the book is the one that I think I used here, but doesn't have to be. But we have, what we find is that we start with a radioactive isotope that's very heavy, a very large one, and it'll break down by an alpha decay, and then by another one. And each time, it'll, after the first alpha decay, it's a new element. Then the second alpha decay, it's a new element. Then a beta decay, a new element, and down it goes. It just keeps breaking down, giving off alpha or beta particles. Those are the most common ones that are given off, until they reach a stable state. So what we want to do is determine, in this case what I've drawn here, we're not at the end, but I say, well, after 6 alpha decays and 3 beta decays, what do we have? So it's just fill in the blank kind of thing as before. We have 92. It's just a little trickier, but these 6 alpha and 3 beta decays are additive, so we can just sum them up. We have 6 and 2, so that's 12. So this is minus 3, so this is 9. And then we have to have that add up to, so this would be 83. Yeah, so 83. And we can look in the periodic table to find out what that is. I don't know offhand. 83 is, where are you? Bismuth, okay. So let me just look at this again. 83 plus 12, that's 95 minus 3, 92, so that looks right. And then on top we have 24 and then 0, so nothing there. And then so this is 2, 14. Alright, so that'd be 2, yep. So that's our isotope. So that's where we ended. After we start with uranium-238, we do 6 alpha decays, 3 beta decays, that's where we end up. So the top part here for the beta decay doesn't change anything, but the bottom changes it in the opposite way that we normally think, because it's a negative number, so you just got to be careful. Now this one is a tricky one. This is the one I usually give on the exam because it just shows that you understand the whole process here. So if I give you the final product and the starting product, then you can fill in the number of alpha and beta particles. Now, because we have 2 unknowns in one equation, it seems like there's no way of determining this, but what we have here, though, is that this beta particle has 0 for the mass number. So when we're doing the top, it doesn't count. So it is actually 2 equations. with two unknowns. Here's the first equation, because this guy doesn't count. So if we do, and if you don't see it, I'll show you in a second when we get done here, but think of this as being missing for when we do the top number. We have 206, and we're trying to get to 226, so this would be 5. So 206 plus 5 times 4, that's 20, so 226. And it doesn't matter what number goes here. This could be 176 million in this slot. It's still 0 on top. This beta particle does not affect the top number. So by doing this, we've determined what the alpha particles are. Now we're down to one unknown, one equation and one unknown, this guy. So we have 82 plus 10, and this comes out to be 92. We're trying to get back to 88, so this must be 4, because that'll be minus 4, and so we have them both. So pretty clever, and as long as you understand that, you can make this anything you want, because you'll solve for the mass number with the alpha particles. Forget about the beta particles, because they won't have any effect. They won't play any part. This is 206 plus 20 plus 0. So always. So that's what we do to solve it that way.